Swayam Prabha. Digital India. Educated India.
This is the first lecture on hyperspectral remote sensing. In this lecture, you will learn basics of remote sensing, the basics of hyperspectral remote sensing, as well as why do we get spectral signature, because that is the base of remote sensing, right? So, let us start this lecture, and the first slide, actually this is the repetition, but still I wanted to show you, because this is the fundamental of remote sensing, where in case of passive remote sensing we are using sun as our source. Sun is illuminating our surface, right, and which is getting reflected, and the reflected energy we capture between 0.4 to 2.5 micrometer wavelength range, whereas in emitted energy we use 2.5 or 3 micrometer to 16 micrometer wavelength range, and there we capture the emitted energy. So, the information will be volumetric. Now, the third case where we are using microwave sensors which can measure the backscattered energy, and here the range is 0.1 centimeter to 1 meter. So, this actually there are three major domain where we are doing the remote sensing, and we are deriving the information about the target, doesn't matter whether it is Earth or any other planet, but this is the fundamental how we are capturing this energy, right. So, if you remember in my first lecture or second lecture, I must have mentioned this, that these three are the source of images, right. So, in normal cases we use mobile phone to capture our activities, and nowadays people are using DSLR, so the resolution of the image will be better. And third case is in remote sensing we are using sensors from a space borne satellite, or in the fourth case we can mount it in our aeroplane or helicopters, and then we can capture our images, right. So, doing this we are basically capturing the either reflected light or emitted light or transmitted light or absorbed light or scattered light. So, these are the fundamental. So, these information can be captured by your specific type of sensor which are working in optical or maybe in microwave domain, and subsequently we capture digital numbers. So, here you can see these digital numbers arranged in an array, right, and basically this is a matrix, and these matrix are basically associated with your pixels, right, and subsequently we display this in image form, right, and this is your output. So, this is the way we are doing our remote sensing. So, let us understand from the beginning that what are the different way we capture this. So, the first one is broadband. I hope you remember the panchromatic images where wavelengths are broad, which is used to generate the image, and this will be a single band image, right. There will be only one image produced for an area, right, and the wavelength, the bandwidth will be more. In the second case where we have discussed the multispectral data, so here in a given wavelength you can have 4, 5 or 6 different wavelength bands, and in between it is allowed to have some gaps, right. So, these gaps are there. In the third case, we have hyperspectral. So, here basically you have hundreds of band, and here you can see there is no gap at all here, right. In the definition itself, hyperspectral says it is contiguous band in narrow band channels, right. So, here you have hundreds of band and there are many bands available here, right. Now, the fourth case where we have ultraspectral. In ultraspectral, again there will be no gap in between the bands, but here the numbers will be in order of 1000, right. Now, in the next case where we are using this hyperspectral remote sensing data. So, basically let us understand how this remote sensing is divided into different image form, like one is panchromatic, multispectral, hyperspectral and then ultraspectral. So, here if we see this hyperspectral remote sensing, so it says that each pixel of the acquired image has an associated spectrum, right. Generally we use this kind of image cube to display our hyperspectral data, right. So, here you can see this is the area and this is the another direction where we have projected all the bands. So, here all the bands are stacked behind. So, here it may be hundreds of band and they are actually stacked behind. Now, here if you want to know what is the property of this particular pixel, then you will have enough information. Why? Because here you have hundreds of band. So, let us consider a case where we are using Hyperion data. Hyperion is a hyperspectral sensor. So, if you are using Hyperion image, then what will happen? You will have 224 image bands, right. So, for each pixel at least you will have 224 values across the wavelength. So, starting from 0.4 micrometer to 2.5 micrometer, you will have 224 values, right. So, if you want to display this, so these are the images. So, this is just for an example I have given. So, these are actually stacked together here in this case. Now, ultimately what is our intention? We want to characterize the object or the surface. So, how we can do that? We can derive the information of individual pixel by deriving the reflected values across the wavelength. So, here you can see this is another example, this is not the actual data. So, if you see for this particular pixel, right, this is the information. So, let us assume this particular sensor is working between 0.4 to maybe 15 micrometer or 16 micrometer, right, and these are the responses. So, if you have such information, then you can definitely characterize your object or material which is better than your multispectral information, because in multispectral you have low spectral resolution, whereas in hyperspectral you have high spectral resolution. So, high spectral resolutions are useful for deriving the composition related information or the internal atomic structure related information of the target, right. So, now you must be wondering that why we actually get this kind of spectral response from a material or from a target, right. So, as I told you, this information can be used to extract the composition related information, right. So, there is a correlation between the internal atomic structure as well as the chemical composition of the target, and because of them only we are getting this kind of spectral signature, right. So, these signatures are having peaks and troughs, and they give the shapes of this spectral feature, right. Now, let us understand why do we get spectra, right. So, first of all, if we are illuminating a surface, then definitely it will eat some energy, that means it will absorb some energy, it will reflect, it will transmit, and then some energy will be re-emitted to our atmosphere, right. And in remote sensing we are capturing these information. So, let us understand why actually these features are coming, right. So, internal atomic structure and composition are the reason of the absorption feature, right. Remember this, because of the atomic structure, internal atomic structure and the composition, you are having this kind of features, right. And these troughs are the places where things are happening. That means, if you get a straight line here, that means nothing is happening, right. But here, if you are getting undulation like peaks and troughs, that says there is some interaction happening between the light which is illuminating this surface and the target. So, the material composition is playing significant role here, right. So, the distribution of electromagnetic radiation emitted or absorbed by the particular object is a function of wavelength. Remember, if you have X composition or Y composition, they have different absorption feature, right. And that is why I have written this is actually like your fingerprint. So, with fingerprint you can identify any particular person, right. That is why now we are using biometric attendance, and there are biometric application where nobody can change your basic information, right. So, here also if you have X and Y material, they are having different absorption feature located in different wavelength regions, right. So, if you want to identify them, then you use those particular absorption features at those particular wavelength region, then you can definitely identify in which material X is present, in which material Y is present, right. So, that is why I have written fingerprint here. So, remember these spectral signature are unique for all the material present in our world, even in other planet, right. So, these are unique information and it can be used as a fingerprint to identify those materials or objects, right. I hope this is clear to you. Now, why hyperspectral is very popular nowadays? Because hyperspectral is a technique, how do we measure the information, right. Basically, if you compare with panchromatic and multispectral and hyperspectral, then you will find the spectral information available in hyperspectral is much more than any of those two. In panchromatic, you have only single reflected or emitted values of the broadband. Then in the multispectral, you have discrete values, and in between you may have some gaps, right. So, I will just, this is for your memory refresh. So, in multispectral you may have 4 bands. If you have selected a pixel, then you will have only 1, 2, 3 and 4 values, and if you connect them, this will be like this. But whereas in hyperspectral you have at least hundreds of band and they are contiguous in nature, that means there is no gap in between. That is why you have continuous spectra here, right, and this can depict or this can capture this absorption feature which was missing here, right. So, that is why hyperspectral becomes very popular nowadays for quantitative analysis, right. So, let us see what advantage we have when we are using hyperspectral compared to multispectral and panchromatic. So, we started with panchromatic. then we move to multispectral, then we move to hyperspectral, and in panchromatic you have only one band, in multispectral you have tens of band, but you have gap in between and the bandwidth can be little bit broad. But whereas in hyperspectral you have hundreds of band, but you do not have any gap in between the bands. So, you have contiguous information about that target across the wavelength, right. So, when we started with panchromatic, we could able to do this object identification, activities and event detection, right. But when we move to multispectral, we could do identification and discrimination, right. Now, we have hyperspectral data, and this hyperspectral data can be used for abundance estimation or characterization of a material or the discrimination also. Obviously, we can do that, right. So, that is why I have written qualitative and quantitative studies. Now, there is one more very unique advantage we have with hyperspectral remote sensing, that is quick and non-destructive and inexpensive technique. Because if you are using a space bound hyperspectral sensor data, then this expense will be very less, because it is for the whole world. Now, it is quick and non-destructive. Why? Because you are not going to disturb the sample or the target, you are just going to acquire the spectroscopic information captured in those particular bands, right. So, here you are not going to disturb or hamper the sample, so you do not have to bring it to your lab. So, as it is in the field, you can measure this information and subsequently you can analyze for abundance estimation, right. So, what exactly we mean by spectroscopy? So, spectroscopy is the study of a spectral feature which is dependent on the wavelength and the material, right. So, it can be object also. Spectroscopy is often used in physical and analytical chemistry for the identification of substances through the emitted or absorbed spectrum. So, if you remember, somewhere you might have heard about XRD, XRF, ICP, they are actually using this spectroscopy technique, right. So, there you have to bring the sample from the field to your lab, then you have to prepare the sample according to the requirement, and then that instrument will give you information, either it is absorbed information or reflected or transmitted information, and that will be available in terms of spectra, spectral signature, and again you will analyze those spectral signature to identify the material composition. So, this is the spectroscopy where we study the spectral features, what is the position, shape, size, right, and then based on that we say this is X, Y and Z material. So, just to refresh your understanding, suppose this is a target, right, and we have a source lamp. This is in case of lab, right, but you can just imagine sun as source of light, and then we can put our sensor here. So, either in the lab or maybe in the field. So, in field it will be spaceborne or airborne satellites or sensors, and in case of lab it will be lab based instruments. So, in both the cases we measure reflected or emitted energy from this sensor, and then subsequently we produce images, right. In remote sensing we basically produce images, and then for individual pixel we derive the spectral signature, because we have contiguous spectral information about that target in narrow channels or bands. So, spectroscopy can be grouped into classes based on the measurement processes. So, there are three major types of spectroscopy. First one is absorption, second one is reflection or emission spectroscopy, and third one is scattering spectroscopy. So, let us see what we mean or what we do in absorption spectroscopy. This is basically related to your lab based instruments. So, it uses the electromagnetic region in which a particular object absorbs, right. So, here a particular wavelength will be used where we know our material, let us assume X. So, X absorbed in 2.5 micrometer wavelength range. So, in absorption spectroscopy, we will use only 2.5 micrometer wavelength range, and then we will see how much energy it has absorbed, and based on that we will identify the material composition. So, after calibration, the amount of absorption can be related to the concentration of various metal ion through the Beer-Lambert's law. Other type of spectroscopy may not require sample atomization because it depends instrument and the technique which you are using. So, in this atomic absorption spectroscopy, the sample was atomized, right. So, it will reach to higher state and then it will come back to lower state. So, how much energy it has absorbed, that you can derive, right. So, it changes with the technique and the instrument. So, do not get confused that sir has told me this, but in this instrument it is happening in some other way. So, this is only in case of atomic absorption spectroscopy. For example, liquid samples, here we generally use ultraviolet visible absorption spectroscopy, right, and infrared spectroscopy is most often performed on liquid, semi-liquid, dried or solid sample to determine the molecular information including structural information. Now, you can see, just imagine how much information you can derive using this spectroscopy technique. So, now you are going to molecule level. So, you can easily determine what is the structure, is there any structural defect in the molecules, right, or is there any composition change, what is their behavior, how much energy they are absorbing, how much energy they are transmitting, right. Those information can be easily identified or studied using this spectroscopy technique. In absorption spectroscopy, we analyze how a sample modifies a electromagnetic radiation interacting with heat. So, basically we see how it is interacting and what is their end result, right. So, change in the intensity of incident light as it passes through the sample is detected. This is used to plot absorbance or transmittance over a wavelength range, right. So, here you have a source light and you are illuminating your sample, and then some amount of energy will get absorbed, some amount of energy will get transmitted depending upon your sample. So, those information can be captured and then subsequently you can plot absorbance spectra or transmittance spectra over a wavelength, right. I hope this is clear. Again, see here, you are going to further study this particular spectral signature, then only you will be able to identify the material composition. So, let us assume if you are going to identify X, so whether X is having any absorbance in these wavelengths, that is fundamental question. So, let us assume X is having absorbance at 0.9 micrometer, right. So, at 0.9 micrometer, if there is any absorbance, that should be related to X, because this is unique information. So now we will look for that, and suppose let us assume this is 0.9 micrometer, then we can definitely say this is because of the presence of X in this particular sample, right. Exactly we cannot correlate directly. So we use this Beer's law, and then we identify what is the composition or what is the concentration of X in this. So that will tell you the concentration, that means it is a quantitative study. Now here the assumption of this particular process is the fraction of light absorbed as light propagates through the sample is proportional to the distance travelled by light through the sample, right. And finally we get this. Now you have seen absorbance or transmittance spectroscopy. Now let us see reflectance or emission spectroscopy, because in general in remote sensing we are using this reflected and emitted light, right. And here we want to acquire the contiguous information in narrow channels, right, and that will tell you the material composition and internal atomic structure. So here if you see, it uses the electromagnetic wavelength range in which a substance reflect or emit. So again you need to know whether your target is sensitive to this particular wavelength range or not. If so, then you can use this particular wavelength range and that particular instrument, and then you can subsequently derive the reflected or emitted spectra, right. In emission spectroscopy, the substance first absorbed energy and then radiates, because that is the fundamental of remote sensing. When a light is illuminating a surface, some amount of light will get absorbed, and to maintain the equilibrium with the surrounding, what will happen? The sample will re-emit those absorbed energy in the longer wavelength region, and that we measure in thermal remote sensing. I hope you remember that part. The energy can be from a variety of source, including collision either due to high temperature or otherwise, and chemical reaction within the sample itself, right. So in emission spectroscopy, this involves excitation of the sample entities that induce emission of light from the sample, right. So here again this light source, sample, and assuming everything is absorbed and there is no transmittance, and we are only using as instrument which can measure the emitted information, and the emission can be because of the fluorescence, phosphorescence and Raman scattering. So this is again for the lab based instruments, but they doesn't qualify the definition of remote sensing, because sample and the sensor both are actually close to each other, and sometimes they are very close. So they are not grouped into remote sensing. So they are having other category like analytical chemistry or analytical spectroscopy technique, right. In remote sensing, basically we use spectroradiometer, right. In spectroradiometer, it is not necessary to touch your sample. So that means we can still validate our remote sensing definition. So spectroradiometer is a device which acquire reflected or absorbed or emitted energy depending upon the configuration of your instrument with respect to wavelength in very narrow and contiguous bands, right. So remember, since beginning I am telling you this has to be very narrow bands or channels and contiguous band. Parameter that describes the capability of spectroradiometers are spectral range. So let us understand this. What do we mean by spectral range? Whether my instrument is sensitive between 0.4 to 2.5 micrometer, or 2.5 to 16 micrometer or in any other wavelength range. So, that is the spectral range of your instrument. So, because here we are using this parameter to define the capabilities of our instrument. So, first thing you have to look is what is the wavelength range in which that spectroradiometer is working. Next is spectral bandwidth. So, what is the spectral bandwidth? Means, let us assume you are having 224 bands between this, right, and they are located like this, very close to each other. So, there won't be any gap, then only it will be spectroradiometer, right. So, if assuming there is no gap in between, right, and this instrument is sensitive from 2 to 2.5 micrometer, right, and you can easily derive. So, what will be the wavelength difference between 2 and 2.5? So, 0.5 micrometer, right. In 0.5 micrometer, let us assume you are having 500 measurements. So, what will be the bandwidth of that? That you can easily calculate. So, that defines what is the starting and end range of your measurement, individual measurement, right. So, this is something like your image band in multispectral, right. So, here you do not have any gap. So, this is the first band, second band and third band, and this has to be very, very narrow, that will be the third point. In spectral sampling, we basically see how frequently it is going to acquire the sample. So, in a minute or in a second, how many sample it will acquire? So, let us say 100 measurement per second or 1000 measurement per second, because these instruments are very sensitive and they can measure 100 measurement in 1 second, and you will get only one average value, or you can have this flexibility, you can save all the 100 measurements data and then you will get 100 values for that particular material across the wavelength, and then you can do average your own. Signal to noise ratio. So, I guess you are familiar with this because I have already covered in many other sections. So, signal to noise ratio indicates what is the strength of your signal or quality of the signal. So, if signal is 100, let us assume this, and noise is also 100, that means both are equal, 50-50. But if you reduce this, let us assume this is 20, that means your signal is 20% and 80% is your noise, right. Then what will happen? The acquired information or the saved data will have more of noise. But if you just invert this one, let us say 80 is your information from the target and 20 is noise, that means this is a good condition because you have more information than your noise. So, that is why we use this signal to noise ratio to define the capability of our instrument. So, these 4 or 5 parameters, they are used for any given spectroradiometer to define their capabilities or their strength, whether they are capable in identifying the material information across the wavelength and what information or what quality you will get, that is defined by these, right. So, spectroradiometer is an optical instrument that uses detector to measure the distribution of radiation in visible near infrared and short wave infrared wavelength region, right. And you can see this. So, these examples I have put here to just get you familiar with all these spectroradiometer. So, this is, I am not supporting any of these companies and their product. This is just for example how they look like actually when you get these instrument in your lab, right. So, these are basically available in the market and they are used worldwide. So whenever you are going to buy or whenever you are going to work with them, then you have to assess their capabilities and their strength or their weaknesses by your own, right. So again, just read this one. This is the definition of a spectroradiometer, and remember, these spectroradiometers are basically very powerful because the same sensor has been placed in the space, right. The same sensor you are getting for your lab. So the same technology if you use to measure the spectral signature on earth and from the space, and if you can correct the space measurement for the atmospheric component, then you can definitely match these two spectras, and then it will be very useful. You can upscale the ground information to the satellite scale, and this is just again to get you familiar what are the things available in these instruments, right. So here this is the fiber optic cable through which your emitted or reflected energy will transfer to your detector, right, and they are fixed. Nowadays it depends instrument to instrument how they have designed. So this is one example where your fiber optic cable is fixed, and in this one most of them are having this internet connection facility. So if you can have or you can connect with a network, then you can access these data sets somewhere else remotely, right. So and this is another attachment which comes with this spectroradiometer, where you can focus your target, because from here this pointer will sense the energy, reflected or emitted energy. This is a fiber optic cable, right, and here you may have some field of view depending upon the instrument. So let us assume here you have X field of view, right, and you are looking for a sample, right. So you have to decide what should be the H, then only it will cover this particular object, and using this bubble you can make sure whether you are looking it vertically or it has some tilt angle, right. So in these spectroradiometers, what exactly we can measure? We can measure spectral reflectance, and why we are calling it spectral reflectance? Because here we will have many bands, maybe hundreds or 200s or 500s band, and in narrow bandwidth, right. So here you will have this kind of spectral signature, right. So suppose this is the one measurement, the next measurement will be just immediately after that. Why? Because you will not have any gap in between the measurements. So that is why you could able to produce this kind of spectra. So that is why we are using this reflectance calculation for many wavelengths. So that is why we are calling it spectral reflectance. Now the next is spectral transmittance. Again we can measure the transmittance, absorbance, then spectral radiance. So obviously because radiance will be captured, and then spectral irradiance, because irradiance is required to convert your radiance into transmittance, absorbance or reflectance, right. So this is your incoming information or incoming light falling on your surface, right. So these are basically speculum panel. So these are actually having this capability to reflect equal amount of light in all the direction, right. So they are isotropic in nature. If you use this particular speculum panel to measure your irradiance, then what we call them? We call them downwelling radiance. Remember? Okay. Now factor which can affect these spectra, whatever we measure through our spectroradiometer, doesn't matter which brand you are using, right. So, what are the factors which plays very critical role? Atmospheric characteristics and stability. This is very important and this is required throughout the measurement. So, atmospheric characteristics means you need to know what kind of component or what kind of atmospheric constituents are present, right. And then stability means there should not be very strong wind or the atmosphere should not change drastically during your measurement, right. Next is sample viewing and illumination geometry. So, if you are having this instrument and let us assume this is the opening of your fiber optic cable and you are looking vertically with some field of view and this is your sample, right. So, the viewing geometry, that means your source is here somewhere, right, or you must be using some other source, maybe halogen lamp or sun. So, this geometry should not get changed during the measurement, right. So, this is very important, that is the source sensor geometry. And then source of illumination. So, if you are using this sun as a source, then with time the intensity changes. So, you have to take care of that. So, you should not plan for the whole day experiment. So, you plan accordingly so that one measurement can be over between very short period of time. Then instrument field of view. So, you should not change the field of view of your fiber optic cable within the or between the measurement, right. Instrument scanning time. So, scanning time is sampling rate. So, if you are using 100 sample per second, then it should be consistent throughout the measurement. Then sample characteristics, because this can severely affect your spectra. So, suppose if this is your target and if you are looking from here, the information will be something different than here. Why? Because in case if you are looking for a rock type, then the composition is not uniform from here, it will be different, here it will be different, right. So, there will be minor change and that could influence your spectra. So, you may get different spectral signature for a given target when you change the position of the acquisition, right. So, this is we called field of view, that sample falling within field of view. And the last one which is very important, wind. So, wind, whether you have a strong wind or calm environment, that also matters a lot here. So, you should make sure that you should not have a strong wind during the measurement, right. Spectroradiometers are very sophisticated instruments. So, you need to follow sets of procedure and you cannot avoid them. Why? Because if you change the way you calibrate or you measure the sample spectra, it will influence your final result, right. So, in this spectroradiometer, basically we use this dark current. And what is this dark current? So, suppose assuming this is my spectroradiometer and this is the fiber optic cable. So, all the instrument components are actually here, right. They are lying in their own position. And since power is involved, because we will start this instrument with battery power or maybe AC power, right. And over the time, all the component will get heated and they will also produce some photons, right. So, it is recommended that whenever you go for measurement, you should keep your instrument on for some time. Then they will saturate and they will start emitting their own energy and that will be consistent throughout the measurement, right. So, what we do, we close this slit and we do not allow any light or any photons to pass from our atmosphere to inside this instrument, and then here we measure what is the photon or what is the energy which is produced by the instrument itself, right, and that we actually measure and that we subtract from our measurement. So, dark current refers to the current generated within a detector in the absence of any external photons. So, we close the external slit and then measure the dark current, then open it again for our measurement. Then white reference measurement, why do we need that? White reference is your spectral panel. So, that is used to measure your irradiance, because when you focus your fiber optic cable towards sun, it will get saturated, right. So, it will not work. So, what we do is, instead of focusing it directly to sun, we use indirectly, where sun is illuminating this surface, there we keep our panel, and then this panel has a property of 100% reflectance, right. So, it will reflect equal amount of light in all the direction, right, and that will give you the downwelling radiance. So, here in a white reference measurement, a material with approximately 100% reflectance across the entire spectrum is called a white reference panel or white reference standard. Using this white reference measurement, you can estimate the reflected energy from your target, right. And the last one is target sample measurement. So, target or sample measurement means the radiance measurement or the reflected energy from your surface or from your target, that will be measured the same way we measured this white reference measurement. But here we use a spectral panel, but here we will remove that and we will directly focus on our sample, right. And once you do that, then you will have this kind of spectral signature. And here this is one example where you have a handheld probe, right. So, this is a contact probe where the source is also inside this, right, and this is illuminating this particular surface, and here we keep this in close contact, and the amount of light which is reflected from this, that will tell you the amount of light incident on the target. Why? Because the same handheld probe will be put on your sample and then we will measure the reflected. And here, why do we have designed this kind of probe? To avoid the atmospheric constituents, because here there is no atmosphere coming into the picture. So, when you have that, you do not have 1.4 or 1.9 micrometer water vapor, atmospheric or terrestrial water vapor signature, right. So, this is when you want to identify or when you want to capture the real spectra of your target without any atmospheric intervention, right. So, now you have understood this spectroradiometer part. So, how do we generate hyperspectral remote sensing data using a spectroradiometer, right, and then we analyze those spectral signature. That is why we are calling them into the spectroscopy category, right. But using this spectroradiometer, you cannot produce a image, right. So, here that new term, which is imaging spectroscopy, has been introduced. What do you mean by this imaging spectroscopy? So, you have already understood this spectroscopy component using spectroradiometer, and there are many other instruments which are actually used to derive the absorbance or transmittance or reflectance or emitted spectra, right. And once we analyze them, that is known as spectroscopy, right. But in imaging spectroscopy, what extra information you will have? You will have images, right, plus spectral information. So, it has both spectroscopy and imaging power, and it will be to acquire spectroscopic information over large area. So that is actually your imaging spectroscopy. So in imaging spectroscopy, we have generated the hyperspectral image where we have narrow band contiguous spectra, right. So the each pixel of the acquired image has an associated spectrum that can be used to identify the surface material and their composition, right. Imaging spectrometers acquires images in a large number, narrow and contiguous spectral band. So it is very important, just understand this one. So here initially we had spectroradiometers, now we are having imaging spectrometers. The term has been changed. Why? Because here we are going to produce images. So here we will produce large number narrow and contiguous bands, right. So typically it is in the order of 0.01 to 0.02 micrometer in bandwidth, right. So just imagine how small they are, right. So once you have that, you can definitely capture all the information coming from the surface. So then you could able to identify all the absorption features which are produced by your target. If you have little bit of the gap between the measurement, then you might have missed this particular absorption feature. But since our imaging spectrometer or spectroradiometers are designed to capture large number narrow and contiguous bands, we are able to identify all these absorption features, right. So there are different terms which are used in remote sensing. So like spectroscopy. So spectroscopy, basically we derive spectral information and then we analyze them, right. So this is only related to your spectra, right. Now next is imaging spectroscopy. So here you have hypercube. This is the image cube of this hyperspectral data, where these are your stacked bands which is behind this main image, right. And next term is hyperspectral remote sensing. So basically these two are same. So sometimes you may find people are referring imaging spectroscopy, sometimes people will call hyperspectral remote sensing. So don't get confused, both are same, right. So let us understand what causes absorption feature in the spectra. So as I told you, the internal atomic structure and composition that actually controls this absorption feature. So whether how much amount of energy they will absorb at a particular wavelength, that is decided by the composition and their internal atomic structure, right. So because of that, we could able to get all this spectral information, and these are basically your absorption bands. So here the shape, size and position, they are very important. Shape, size means shape is whether this is broad absorption feature or this is very narrow, right, and whether they have any doublet, this kind of a spectral feature, right. Then size is clear, shape is clear. Now position, whether they are coming at this particular wavelength, this particular wavelength, this particular wavelength, this particular wavelength, that actually tells about the material, whether it is X, Y or Z, right. So that's why I have mentioned this is basically your fingerprint, right. So it is unique for all the materials. So here not necessary you will find only one absorption feature and you can say this is X. So you can have set of absorption feature which can be used for X, Y or Z material. So because in nature there are n number of materials, right. So for them absorption feature cannot be unique by identifying only one particular absorption feature. So what you have to do, you have to look for different sets So like maybe if in one example you can just see this, maybe here you are getting one absorption feature, right, and the next is coming here. So if you find these two, that tells about the X material, right. So it is very important to study these spectral behavior and their composition of the material. So accordingly you have to identify what is the absorption feature for X, whether it has only one absorption feature in this particular wavelength range or it has multiples of absorption feature, which should be studied together. Then only we can say this is X, Y and Z. So there are two different processes which is happening, right, and because of that only we are getting these spectral signatures. So one is electronic and the next one is vibrational process. So if you know what is the electronic and vibrational process happening within your sample, then you can identify or you can directly tell at what wavelength they will give the spectral signature, right. Now let us start with the electronic process. In electronic process, basically isolated atoms and ions have discrete energy states, and absorption of photons of a specific wavelength causes a change from one energy state to another one, right. So the next energy state will be the higher one because it has some extra energy. Emission of a photons occurs as a result of change in an energy state to a lower one and can be observed in VNIR wavelength region. So here you can see we have given some extra energy, right, and that has resulted to change the energy state to the higher one, and then ultimately what will happen, it will settle down and then it will re-emit or it will release the extra energy, and that can be observed in VNIR wavelength region. When a photon is absorbed, it is usually not emitted at the same wavelength. So as I told you earlier also, suppose if it is absorbed, it will be emitted in the longer wavelength region, right. For example, it can cause heating of the material resulting in gray body emission at longer wavelength. Electronic transition produce broad absorption feature that requires high energy level and occur at shorter wavelength. So remember, these electronic processes result in short wavelength absorption features, right. So if your material is sensitive to this electronic process, then you will find absorption feature in the shorter wavelength. So the first one is crystal field effect. This is inside this electronic process. So what is happening here? The common electronic process occur in the mineral spectra due to unfilled electron cells of transition element like nickel, chromium, cobalt, iron, etc. Transition element have identical energy in d orbitals in an isolated ion, right. The energy levels split when the atom is located in a crystal field. Crystal field describes the breaking of orbital degeneracy in transition element complexes due to presence of ligand, right. Splitting of orbital energy state cause electrons to move from a lower level into a higher one. The energy levels are determined by the valence state of the atom. For example, whether it is Fe2 plus or Fe3 plus, its coordination number and their symmetry, right. So the energy levels are determined by the valence state of the atom. So it is different for 2 plus iron or Fe3 plus, right. The crystal field varies with crystal structure from mineral to mineral, thus the amount of splitting varies and the same ion like Fe2 plus produce different absorption. So now it is different for Fe2 plus and 3 plus. So for the same ion you have different valence state, right. and because of that also you are getting different position of the spectral feature. So, just imagine how accurate information it can give you, right. Due to this reason, specific mineral identification possible from spectroscopy. So, this is one example where I have put iron. So, iron does not matter whether it is from the same iron, but the valence state is different. So, it is producing different absorption feature. So, here you can see this example where reflectance spectra of two pyroxenes shows the change in Fe2 plus absorption bands, right, position and shape with composition. This I have taken from this reference Clark et al 1993b, right. The 1 micrometer versus the 2 micrometer band position describe the pyroxene composition. So, remember this 1 micrometer versus 2 micrometer band position describes the pyroxene composition. Why? Now, you have to analyze this spectra and you can just correlate with your band math, right, band ratios concept. Now, you see why we can use this particular combination to highlight this pyroxene. The next process in electronic is charge transfer. So, this is known as charge transfer absorption or inter-element transition, right. So, the absorption of a photon causes an electron to move between ions or between ions and ligands, right. It can also occur between the same metal in different valence state, such as between Fe2 plus and Fe3 plus. In general, absorption bands caused by charge transfer are diagnostic of mineralogy. So, here it is very important, using this absorption band caused by this charge transfer can be used in mineralogy. Now, there is a slight change in mineral composition and we have a new name, right, in earth sciences, in geology. So, just imagine how accurate information it can give you, and it is giving us. So, because of that reason, hyperspectral remote sensing or imaging spectroscopy is very useful. Their strength are typically hundreds to thousands of times stronger than crystal field transition, right. Here, this is the example where you have reflectance spectra of iron oxide hematite and iron hydroxide goethite. Now, here you can see for goethite and hematite the spectral signature has been changed, right, with this slight change in the composition. In another process where we have this conduction band, here in some mineral electrons may have two energy levels, right, it is also possible. So, the conduction band where we know that this is the higher level, the electrons move freely throughout the lattice, whereas in the valence band, which is the lower level, and electrons are attached to individual atom, right, and the difference between the energy levels is called the band gap, and it occurs only in visible region, right. So, this is the example of conduction band where this sulfur and cinnabar both are used, showing conduction band in the visible wavelength region. So, here you can see how they are looking differently in the spectra, right. The next one is color center. A few minerals shows color due to absorption by color center, right. A color center is caused by irradiation, and that is caused by solar UV radiation, right. I hope you know this, that in nature there are minerals which are available in some defective form, right. So, if you have defects in the lattice of those minerals or those crystals, that can result in producing different energy levels, right. So, this is discrete energy level and that can be caused by this color center. Let us see the next part of this process, that is the vibrational process, where we study the molecular bonds, right. So, the bond in the molecules or crystal lattice are like a spring with attached weight, the whole system can vibrate. So, here if you visualize them, it will be like two molecules attached with a spring like structure and they are vibrating. So, either in this direction, right, or here also. So, it is possible. So, the frequency of vibration depends on the strength of the each spring or bond and their masses. So, suppose if this is heavier and this is lighter, then this won't move and this will vibrate, and if the spring is very soft, then it will vibrate more, but if the spring is basically very strong, then it will vibrate less. So, the spring is basically the bond which is present in the molecule, whereas this masses are actually elements. So, here it depends on these two, what is the bond and what is their masses, right. So, here you can see this vibrational process can result in bending, systematic stretching and asymmetric stretching. So, I have a animation page for you that you can see all these things in the better way. Here this is z axis rotation, this is y axis rotation and this is translation motion, right. So, let us visualize this with the help of this animation. So, here this is for the systematic stretching. So, here you can see how they are vibrating with each other, right. The next one is asymmetric stretching and third one is scissoring, then fourth one is rocking, then wagging and the last one I have is twisting, right. So, this is available in Wikipedia, you can visit this Wikipedia, they have very beautifully defined and made this animation. So, let us thank Wikipedia and whoever has put that information in the Wikipedia. So, in vibrational process, the fundamental frequency, that is this nu. So, it is basically 3n minus 6 for a molecule with n atoms. So, this is very important. This is a rule to identify how many fundamental frequency we can have for a given target, right. And overtone and combination, these are basically, it occurs at roughly multiples of original fundamentals. So, multiples of fundamental. So, if a molecule has vibrational fundamentals like V1, V2, V3, then it can have overtone at approximately 2V1, 3V1, 2V2 and combination at approximately V1 plus V2, V2 plus V3, V1 plus V2 plus V3. So, these are few examples, right. So, what I mean to say, the fundamental frequencies can be identified using this formula, whereas the overtone and combination can be estimated by this information that they occur roughly multiples of the original fundamentals, right. So, subtraction is also possible here. So, here you can have V1 plus V2 minus V3, right. So, for example, here you have. Now, the overtone and combinations are 30 to 100 times weaker than the last, right. Hence, the features will be more difficult to sense. Vibrational absorption occur at longer wavelength with deep and narrow features. So, remember, electronic process gives absorption feature in the shorter wavelength, whereas the vibrational process results absorption feature in the longer wavelength, right. The water molecule, that is H2O, has n is equal to 3. So, there are 3n minus 6, which is basically 3. So, the water molecule will have fundamental frequency in 3 position, right. So, here this is one example where you have this calcite and dolomite. So, here you are seeing the small band shift due to change in the composition between these two minerals, right. The label change is because of the calcite has a small grain size, right, and calcite higher in reflectance than dolomite. So, the reflectance will be high for the calcite. And the effect of terrestrial or atmospheric water in the hyperspectral remote sensing data. Suppose if you are generating a hyperspectral data from space, what information or what error this terrestrial atmospheric water can introduce, right. So, in the spectra, terrestrial atmospheric water shows very strong absorption at 1.4 and 1.9 micrometer wavelength region, which makes this region unusable for remote sensing of Earth surface. Remember, this is I am telling when your target is surface, but for atmospheric people this error can be the data, right. So, here if you see the spectra which is acquired from this space, so basically we have captured the hyperspectral image, then we have generated the spectral signature of a given pixel, and there you can easily find the missing data. Why? Because we have removed the noises. So, initially it was here, it was like this, right, that we have removed because our target is different, our objective is different. So, we do not have to analyze them. So, we can simply remove them and rest data we can analyze. But for a person who is interested to study this terrestrial or atmospheric water, then he should remove all this, right, and he should keep only the 1.4 and 1.9 information, right, and this will help him to study or identify the concentration of terrestrial or atmospheric water. This can be considered as limitation or advantage depending upon our application. So, I will end my lecture today here, and you can go through these two. So, this is one book which is Basic Principle and Prospective Application by Freek D. Vandermeer and Stephen M. D. John, right. And this is my paper where I have explained the basics of hyperspectral remote sensing. So, this is a review paper on this technology. So, if you want to understand more or if you want to start your research in this area, I will recommend you can start reading these two references, and there are many other books available, that is also good, but you start with this and subsequently you can explore yourself. Thank you.